Good afternoon, everybody. Welcome to our breakout session. My name is Minhan. I'm a software engineer on the Kubernetes Engine networking team. So we're here to talk about container-native load balancing on Kubernetes Engine. We have 3 items on the agenda. First, how Google Cloud treats containers as first-class load balancer endpoints. And second, how Kubernetes Engine natively supports advanced level 7 functionalities. And finally, we have a surprise session with something coming soon. In 2015, Kubernetes 1.0 was launched. Google brings its container experience of over a decade to the industry. As an open source project, Kubernetes focused on portability. It uses the lowest common denominator technology. That includes load balancing. In 2015, most load balancers only work with virtual machines and bare metals. They do not support containers natively. Load balancing solutions for Kubernetes usually involve some kind of proxy to pass traffic from the load balancer to the container. In summary, when Kubernetes was born, load balancing solutions was not optimized. Imagine you are a customer with multi-tier application. I have my project on Google Cloud, I have my virtual network in my project, I have my Kubernetes Engine cluster running in my virtual network, I have my workloads running in the cluster. Now, how do I expose my services to the internet? The answer is the Kubernetes service abstraction. So the Kubernetes service abstractions provides 2 major functionalities. First, it selects a group of backend using label selectors. Second, it provides static access point to these backend pods. On the left, there's a sample service specification. Its name is my service. It selects pods with label key app equals to app and value equals to my app. It exposes port 80 and its type is cluster IP. For external traffic in particular, there's no port type service and there is load balancer type service. Logically, the diagram in the middle represents how the traffic flows. The traffic first arrives at the service abstraction, represented by the red icon, and then the service will deliver the traffic to one of the backend pod, represented by the blue icons. On top of service, there's an Ingress resource in Kubernetes. It represents a level 7 load balancer. A no port type service allocates a static port across all cluster nodes. Traffic flowing to the no port on any VM or any node will be forwarded to one of the backend pod. This model is very easy to understand. There's no external dependency. Users just need to run the standard open source kubeprox to have this feature. The downsides are obvious. There are only limited number of node port within the cluster, and the clients need to adjust to node IP changes. And node port only provides basic load balancing algorithm, basically spreading the traffic randomly. All these results into suboptimal load balancing. In Kubernetes, there is a cloud provider abstraction layer. This layer makes it easy to integrate Kubernetes API with different infrastructure. This makes Kubernetes API portable across platforms. When user creates a load balancer type service, a real load balancer will be provisioned. It usually comes with an external virtual IP. Traffic first flow to the virtual IP. It arrives at the load balancer, and the load balancer will deliver the packet to the Kubernetes service. In most integrations, the load balancer will just deliver the packet to a no port type service, and the service will further deliver the packet to the backend pods. Kubernetes services are level 4 constructs. In order to support level 7 functionalities, Ingress was proposed. Ingress supports popular level 7 functionalities like TLS termination, URL path mapping. There are many Ingress implementations. On Kubernetes Engine, it utilized Google Cloud Load Balancer to implement the Ingress API. Conceptually, Ingress traffic first arrives at the Ingress layer. That can be a Google Cloud Load Balancer. Then the level 7 functionalities kicked in. TLS termination and URL path mapping, and the load balancer will deliver the traffic to the corresponding service, and the service will take it to the backend pods. We have briefly walked through the Kubernetes API constructs for load balancing. Although the API seems straightforward, but the underneath data path can be very, very complex. To understand what is container native load balancing, we need to take a closer look at the data path. Here is a typical Ingress setup on Kubernetes Engine. All other cloud providers have some similar setups. When user creates an Ingress, Kubernetes Engine will create a Google Cloud Load Balancer. And the Google Cloud Load Balancer will point to an instance group. The instance group contains all cluster nodes. And kubeproxy is responsible for forwarding traffic to the actual backend pod. The name of kubeproxy is quite misleading. It's not a real proxy. It programs IP tables and asks the Linux kernel to do its job. So this setup results in suboptimal load balancing. As you can see in the animation, the blue dot represents the incoming traffic. Load balancer sends packet to the virtual machine, and kubeproxy programs IP tables to intercept traffic from the load balancer. Then the IP tables magic took place. IP tables randomly select one of the backend pod, perform network address translation, port translation, and finally send the packet to the destination pod. Because the backend pod selection is randomized, the IP tables can select a pod on a different node. That will result in a second network hop. For the response packet, it will reverse the incoming data path. So the pod will send out the response packet. The packet will first arrive in the forwarding node. On the forwarding node, IP tables and contract table will undo all the network address translation and port translation. And then the packet will return back to the load balancer. So with all these, it's very, very complex. There's a lot going on just to deliver a packet to the container. Now, we are proud to announce container native load balancing using Network Endpoint Group feature on Google Cloud. Network Endpoint Group feature allows Google Cloud Load Balancer to target containers directly. Containers become just another endpoint. As you can see in the animation, there's no IP table magic, there's no proxy involved, no need for the complex network address translation, and of course, there's no second hop. Every connection is established directly between the load balancer and the backend pod. So let us have a side-by-side comparison. The data path becomes much, much cleaner. So what difference does it make? Network Endpoint Group makes load balancing for containers as efficient and as easy as load balancing for virtual machines. So let's summarize. Network Endpoint Groups makes container first-class citizen on Google Cloud Load Balancer. It opens the door for native container support for many load balancer features, such as traffic shaping, advanced load balancing algorithms, and many more. Take traffic shaping as an example. Without Network Endpoint Group, load balancers can only do traffic accounting per virtual machines. With the secondary load balancing happen on the virtual machine, load balancer loses track. Switching traffic between VMs doesn't result in switching traffic among the actual backend pod. With network endpoint group, load balancer gains the visibility into each traffic flowing to every containers accurately. Then traffic shaping is achievable at the container level. Secondly, data path is optimized. There's no longer any proxy between the load balancer and the backend pod. That eliminates the second network hop. This reduces the latency and removes the overhead for the complex network address translation and results as a predictable network performance. Finally, tools that integrated with Google Cloud Load Balancer gets visibility at the container level automatically. Load Balancer health check can retrieve accurate health status per container. Without network endpoint groups, Load Balancer sends the health check to the virtual machines, and virtual machines forwards the health check request all over the place. That makes the health check result unreliable. With all that, I would like to introduce my colleague, Manjot.
Thank you, Minhan, for making load balancing boring again. Minhan just gave us an overview of how our load balancing is becoming more container native. I will now touch upon how our network services are also becoming more container native. Google Cloud Platform network services have the mission to deliver services that are smart, secure, and modern on the Google Cloud Platform and other clouds. We bring these strengths to your Kubernetes Engine deployments via Ingress and a host of other feature improvements. We all know that Ingress is your one-stop shop for configuring all your L7 needs, including your global HTTPS Google Cloud Load Balancer. Up until now, you could set your host path routing rules via Ingress to be set up at the HTTPS Google Cloud Load Balancer using Kubernetes native Ingress API. We have been working at Kubernetes Engine to bring Kubernetes Engine networking at par with Compute Engine and establishing containers as first-class endpoints. With these changes, you will be able to use the Kubernetes Ingress API to configure L7 security, authorization for your employees, and use a globally distributed caching infrastructure. Configure security policies for defense at scale against distributed denial of service attacks with Cloud Armor using Google's global infrastructure and security systems. Use Cloud Armor in your Kubernetes Engine deployments to protect against malicious attacks at the edge and restrict access to the load balancer. I would recommend going to the session on Cloud Armor by Prajakta. Control access to your internal applications at application-level granularity using identity-based access control with identity-aware proxy. Cloud IAP, or identity-aware proxy, lets you establish a central authorization layer for all your applications accessed by HTTPS so that you can use an application-level access control instead of the older network-level firewalls, which gives you an all-or-nothing application-level access-level granularity. Third, leverage a globally distributed caching infrastructure for all your low-latency applications using Cloud CDN. Caching content at the edges of Google's network infrastructure using our over 90 CDN locations will provide you faster delivery of your content to your users while reducing serving costs. Together with the above capabilities, you can build applications on Kubernetes Engine that are smart, secure, and modern. We will demonstrate the integration of these new capabilities and how Ingress on Google Cloud Platform becomes the single pane of configuration for all your L7 needs. Let's jump into a little more detail on how we can do that. So we introduced a new concept called the backend config. But before we do that, let's jump into a little more history. As you might already know, Kubernetes Ingress API is the open source and portable way to express your L7 configuration. Since it was meant to be portable, the only way to have provider-specific information was through Ingress annotations. This made the integration of new features either dependent on the approval of the community, affecting the speed of overall development, or an overpopulation of annotations on your Ingress definition. Maintaining this delicate balance between provider-specific information and an Ingress portability is not an easy question to answer. So backend config aims to address exactly that problem. We introduce backend config to specify configuration on a per-service basis. Use backend config for your Google Cloud Platform network services like Cloud Armor, Identity-Aware Proxy, and Cloud CDN to begin with. Backend config is a new Kubernetes custom resource that is a Kubernetes native concept and is specific to Google Cloud Platform. Backend config lets you specify configuration for all your services without the need of polluting your Ingress definition with too many annotations, as was the case in the past, and which makes your Ingress definition non-portable. This simplifies your experience with the Ingress API. There's native integration with all the GCP network services, giving you a host of benefits, and service configuration becomes a first-class concept. You have the flexibility to specify configuration pertaining to a single service rather than an all-or-nothing for your whole deployment. You can hook up your service definition using backend config to use all these network services. Now, let's move on to some of the new features that we have for Ingress on the Google Cloud Platform. Minhan already mentioned that Ingress can be used for TLS termination. Today, we announced the availability of multiple TLS or multiple SSL certificate support through your Ingress definition. Instead of the older way of bundling multiple domains into a single certificate or having multiple Ingress definitions that adds overhead. We also try to ensure at Kubernetes Engine that your Ingress remains competitive in the integration of new protocols and new technology. Ingress now supports HTTP2 protocol, which is designed to improve performance over its predecessor, which is the HTTP1 protocol. Support for HTTP2 enables you to use gRPC, which is an open source framework for remote procedure calls based on the HTTP2 standard. gRPC enables you creation of performant, scalable APIs and microservices in many programming languages and platforms. To summarize what we have mentioned till now, we bring you a host of new capabilities and features to configure at L7 via Ingress on the Google Cloud Platform. The concept of backend config, which lets you set configuration on a per-service basis without the need of polluting your Ingress definition with too many annotations, and gives you flexibility to specify things on a per-service basis rather than for your whole deployment. Native integration with Google Cloud Platform's network services, which lets you get a host of benefits, including security at L7 using Cloud Armor, identity-based access control for your applications via Identity-Aware Proxy, and a globally distributed caching infrastructure using Cloud CDN. Ingress on the Google Cloud Platform also lets you use multiple SSL certs for your deployment and use new protocols such as HTTP2 and gRPC. With that, I'll hand over to Bowei, who is the Kubernetes Engine TL, to show you a host of new features.
OK, hello. Thanks, Manjot. So Kubernetes Engine makes it easy to create Google Cloud load balancers, and it's full of features, as you have seen in the previous slides. But we've heard lots of questions about how to extend your applications using Ingress across multiple clusters, whether it's for fault tolerance or to optimize latency. And what I'm going to show you is a sneak peek of something that we're currently working on. So suppose you create an app. You deploy it on Kubernetes Engine in North America, and you have users coming to your cluster. Now your app gets very popular, actually popular all over the world. Now you have users coming from London, Singapore, all over from Europe, Asia, but your application is still being served from a North American cluster. Note that the Google Cloud Load Balancer will terminate your connections at the Google Edge. You'll see there's a Google Edge in North America, Europe, and Singapore, which gives your users the benefits of low latency protocol termination. However, the application will be still served from your North America location, so the end-to-end application latency may be higher for some users in the world. Now, today, you can geo-localize your application by using DNS. With this setup, you can create an ingress for each cluster you're serving in the region that you want it to serve, and then have a different VIP for each, and put that virtual IP in your DNS record. While this gives you geolocalization, as you know, DNS has suboptimal load balancing and failure over characteristics. In addition, you need to maintain multiple copies of the Ingress resource and synchronize them among your clusters. Also, you need to set up GeoDNS. So we are excited to announce an upcoming feature in Kubernetes Engine, which is multi-cluster and multi-regional Ingress support. With this feature, you'll be able to write one Ingress definition and use Google Cloud Load Balancer to distribute traffic among the clusters from a single Anycast IP. Now, as your user base expands, say worldwide, you will be able to add clusters in each region where you will have users, following your user population as needed. As you see from the diagram, there'll be a single virtual IP that will be programmed into your DNS, and traffic from each of your clusters will be routed to the closest one. In fact, if capacity is exceeded or if a cluster goes down, your user will be routed to the next best destination automatically as failure is detected. Now, actually, let's take a hands-on look at some of the details about how this will work. So give me 1 second. OK, so here we have a dashboard that is wired up to a live instance of the multi-cluster, multi-regional Ingress. And as you see, following the workflow from before, we have a North American cluster. And most of our users are from North America, so they experience acceptable latency. We have a few users from Asia, but not too many. Now, as we increase the traffic because our app got super popular, we get a lot of users from Asia. But you'll notice that they're still hitting the North American cluster. With multi-cluster and multi-regional Ingress, we can actually add a cluster. You see that we added a cluster in Asia, but we haven't updated the routing. Now, finally, we will update the routing so that this cluster is included in the load balancer. And as you see, the users in Asia will go to the Asia cluster, and the users in North America will go to the North America cluster. Now, let's poke a little bit in terms of what this actually looks like. So here is the Ingress definition for this setup. You notice that it is just the vanilla Kubernetes Ingress definition. And in fact, when you go and look at your network service in Google Cloud UI, you'll see that it sets up a single virtual IP. And the difference is you have two backend services, one of them in Asia and one of them in North America. Finally, let's see what happens for your users, right? Your users, we have clients in Asia and we have clients in North America. So here's an access log that's been aggregated across the clusters, showing where the user request was coming from and which cluster is served. And as you can see, requests coming from North America are served by the North American server, and requests coming from Asia are being served by the Asia cluster. Now, switching back to the presentation. OK, so what are the benefits of multi-cluster and multi-regional support? So notice you have a single configuration for your global applications. You will use a single standard Ingress definition that you already use to define your HTTP applications. This definition will be used to configure a global multi-cluster Google Cloud Load Balancer, giving you one place for configuration and status. The multi-cluster, multi-regional ingress will use network endpoint groups to address your cluster endpoints. And as you saw earlier, this has all the advantages of container-native load balancing. You have accurate health checks, better load balancing algorithms, and optimal network performance. And finally, and the most straightforward point, you have geographical load balancing and high availability. And using this feature will make your Kubernetes apps and services globally distributed. So, as you saw in this talk, there's a little bit of history about where container load balancing was, and some indications of what we think the final form should be. And the final form should be container-native load balancing. What is container-native load balancing? First and foremost, it means that containers have optimal network transport. Load balancers are container-aware. There should be no difference whether your workload uses containers or VMs. It should just work. Second, your container workloads can use Google Cloud Load Balancer feature set. For example, security, caching, authentication, in a Kubernetes native way using Kubernetes resources and configuration. Finally, coming soon, Kubernetes Engine will support extending load balancing across multiple clusters and regions, giving your applications global reach and high availability. We want to make it so that any choice of technology, whether it's containers or VMs, runs the best on Google Cloud. And container-native load balancing is a piece of that puzzle. Thank you.